to, the final goal of this series of talks was to give a proof of the recent result of David Asbrough and mine that Martin's maximum double plus implies the axiom star. We didn't yet even introduce the axiom star, but the plan for today is to prove something whose proof then may be easily generalized to give this result. So we will see how everything goes, but the important thing is that we are getting a flavor of the area and of what's going on in the relationship between these things. So the plan for today is as follows. Yesterday in the later parts we talked about iterating V by a total measure on V. We showed that V is iterable in this respect. Then we discussed measures which are external to a given universe. In particular, if you have a given real X, you look at L of X and you might have an external measure in the sense that there is an elementary embedding from L of X into L of X. You derive a measure from it, and then you can iterate the structure L of X together with that external measure. You can make sense of that, and this thing turns out, we didn't prove that is iterable. This is equivalent to the existence of X sharp. And then we started discussing a different way of taking of obtaining external ultrafilters on a given inner model. Namely, we discussed, well, ideals and forcing with the positive sets of ideals. We gave a characterization, or we defined saturatedness for an ideal. Our particular interest was the non-stationary ideal on omega 1. So we defined what it means to be saturated. We gave a characterization of NS omega 1 being saturated. And then we introduced the concept of precipitousness for an ideal, in particular our main interest, again, the non-stationary ideal on omega 1. And just to remind you, an ideal is precipitous, so that if you force with the positive part of the ideal, maybe I should, just to remind you on the side, if I is an ideal, let's say a normal uniform ideal on kappa, I plus was the positive sets, that's everything which is not in the ideal, so in some sense which is not small. And you can construe I plus as a forcing by saying that if S and T, let's say, are in I plus, then we say that S is stronger than T. I always have to draw a diagram to remind how it goes. If that section here is small, so if S without T is in the ideal. Basically, S is supposed to be a subset of T, but modulo I. Not T, this is not in, I'm sorry. This is an I, okay. Okay, so we can force with that. We saw parts of the proof, and the rest is not hard, that if you force with that, you get if you force over V with such a thing, you get a V ultrafilter, so you can take the generic ultra power, or you can take the ultra power by that filter you get by forcing. That's called a generic ultra power of V. Generic because it only exists in the forcing extension. And the ideal is called precipitous. So this is all repeating what we did towards the end yesterday. If and only if the ultra power of V by the generic is always well-founded, where G is V generic for forcing with the positive sets of I ordered in this fashion as it's defined up there. Okay. Okay, so this is to remind you what we did towards the end yesterday, defining precipitous ideal. So now today we want to start out by, I think I already wrote it down, but we will write it down again and then prove it. So we show a characterization of precipitousness Okay. We will show that V, if you force over, so if you fix a precipitous ideal in V and then you force with it, so the outer power is well founded, and then you take the outer power, so the target model may be transitivized, so and then by elementarity, in the outer power, you have a precipitous ideal again, so you may repeat the process, and we will prove that you actually also at limit stages you take direct limits, and we will show that at direct limits you also don't run into a problem. So we will show that V is generically iterable. With respect to precipitous ideals. So what I mean by that, right, is you have this precipitous ideals, you take it generic, you take the generic outer power, and then you do the same thing over and over again. You do it as long as you, of course, there is a limitation, right? I mean, you always need to pick generics, and the generics exist only outside of V. So usually the way you think of it is that, first of all, you pass from V into a generic extension where you collapse a large cardinal. I mean, not a large cardinal in a technical sense, just a cardinal high up enough. And then this generic extension will provide you generics for the relevant forcings up to a certain point, at least up to the omega-1 of that forcing extension. Okay, so then finally a discussion which I promised for, have been promising for a while, a discussion of effective counterexamples to the continuum hypothesis. We will introduce what it means for a set to be projective, what it means to be definable over H omega 2, and we will give a lot of examples. A particularly important point class here is pi 2 over H omega 2, it turns out. Okay, we will give an illustration of the relationships between these various pi 2 over H omega 2 statements, which are important in this context. Namely, I want to prove that a principle which we will call admissible club guessing that this implies that U2 is equal to LF2, and we will introduce LF2 or omega 2, you know what it is, it's the second uncountable cardinal. U2 will be defined. We already discussed it a little bit sharps. I just mentioned it, that we discussed non-trivial elementary embeddings from L of x into L of x. If x is a real, that's equivalent to the existence of x sharps. And in terms of sharps, you can define the second uniform indiscernible. That's called U2. We will introduce that. And then the plan is that the last thing today, I hope that we will get there, and if not, the world is not going to collapse. So we prove that admissible club guessing follows from MM. So in particular, it will follow from MM that U2 is omega 2, and that actually, as we will discuss, is an effective counterexample to the continuum hypothesis. And the proof of that last thing there is a much more elementary proof how you could organize this proof. But I want to prove it in a more complicated way, and I want to do it on purpose. Namely, the more complicated way, I'm going to prove that thing will be so that it easily generalizes to prove other things. For instance, to prove star from double plus. Or if you want, you can use it to prove some kind of version of the omega conjecture, namely that certain statements which are consistent in a strong way can actually be forced, and therefore under forcing axioms are true. Okay, so the last thing I will prove in a more complicated way, it will be kind of inspired by the proof of David Asper and myself of double plus implies star, which in turn builds upon forcings which I developed with my student Ben Claverie and also Philipp Döbler, which in turn builds on a forcing by Ronald Jensen, which is called L-forcing, which in turn has a precursor, I guess, forcing maximally consistent theories in model theory. Okay, anyway, this has a long history. Okay, so this is anyway the plan for today. Okay. Okay, so first topic, precipitous ideals. So I already wrote on the theorem, and the characterization of saturated ideals we saw towards the end yesterday, and also this characterization of precipitous ideals I think is not that well known, and I'm not sure if this is written down somewhere, so I cannot really give you a reference, I think. What's going on? The following statements are equivalent. The first one is that the non-stationary ideal on omega 1 is precipitous. And the second statement is that the set S, you look at all the countable substructures of H theta, where theta is big enough. I never write it down, so theta is always supposed to be some big cardinal, large enough so that the arguments which you're considering goes through. You would like to write just V here, but you're not allowed to do that because in CFC you cannot prove that there are fully elementary substructures, the proper substructures of V. So if you transitivize and you define G as the collection of all, now let me write Y, element of the power set of omega 1 of M, which exists inside M, so that omega 1 of M is an element of sigma of Y. You can write it down without collapsing, but I find it more handy or more readable if you write it down that way. Then G is M generic for forcing with the version of M of the positive sets of the non-stationary ideal. So you take this thing, okay? So this thing, this is the set you want to consider, and you say that this set is supposed to be projective stationary. And we defined what it means for such a set to be projective stationary yesterday. This means that for all t subset of omega 1 stationary, the set of all x's in S so that x intersect omega 1 is in T, so that that's always stationary. So that's a strong form of this set which lives on h theta to the omega to be stationary. Okay. Okay, maybe I'm not giving really the full proof of this thing, but I'm giving you a sketch of the proof, and I invite you to fill in the details. And if there are any questions, we can dig further and go further into details, and otherwise this will be some kind of exercise to fill in the details. Okay, so the proof. So let's do this direction first. Okay, so let's fix a stationary subset of omega 1. Okay, and we have to prove this statement in the box, assuming that the non-stationary ideal on omega 1 is precipitous. Because it's precipitous, we can force with the positive sets of that non-stationary ideal and get a well-founded alpha power. Well, it's every generic alpha power is well-founded. So what we may do is we may simply put T, which is a stationary set, so it's a positive set from the point of view of the non-stationary ideal. We may pick a generic which contains T. So let G, maybe G is not a good name because G also shows up. Let capital G be V generic for forcing with a non-stationary ideal on omega 1 such that T is actually in the generic. Okay, so this will give rise to a generic elementary embedding J from V into the alpha power of V by G, let's call it M. And because T is in capital G, by the theory of how alpha powers work, this will mean that omega 1 of V is an element of J of T. This follows from the fact that T is in G. Okay, so now if we draw a picture, so we have V here, we have M here, we have this elementary embedding which exists in the generic extension. There is omega 1 here. This is the critical point of the embedding, because the measure which you get externally by forcing and which we can read off from capital G is a measure on omega 1 of V. So this is the critical point. Okay, so we are interested in certain substructures of H theta. So there is theta is somewhere up here and it's large. Okay. Okay. So what we want to do now is we can say for some reason or other, we may assume without loss of generality that from the point of view of M, theta became countable. You could, for instance, force over M just with a collapse and make theta countable. So the part of right in some outer model to M, V up to, well, not in some outer model to M, theta is countable. Okay. Now let's look in V of capital G. Let's look at the structure. Let's look at J, the pointwise image of J of H theta of V. Right? It has all the properties. It is kind of an element of the image of our set curly S, right? So at least in that extension of M where theta is countable, right? I mean, what properties does this thing have? Okay, this is a substructure, an elementary substructure of the Hj of theta of M. Okay. Moreover, so that's a countable substructure. Moreover, omega 1 of it, I'm sorry, omega 1 of M intersect this thing is exactly the omega 1 of V. Okay. And capital G, if you look at the transitive collapse of that thing, it's exactly H theta of V. So capital G is generic over it because this is how you picked it. Okay. So external to M, there is this substructure, namely this thing, which satisfies all the properties you want. And then there is an absoluteness argument, like you can organize it as a tree argument or some other kind of ways to organize the absoluteness argument, which says that by absoluteness, M can also see a substructure capital X like that with all the properties. Namely, M can see a countable substructure of its H sub J of theta, so that everything is true what we want, namely that the intersection of that substructure with the omega 1 of M is the omega 1 of V. And we have a generic over the transitive collapse of that substructure, so that if you take the generic alpha power, you can at least embed it into the H sub J of theta of M. And this is a statement which is then true over M, and then you may pull it back. Okay, so in the end, what you get is that V can see that there is a countable substructure of H theta, so that also the intersection of that countable substructure with omega 1 is in T. This is also true by elementarity, because the original substructure intersected the omega 1 of M is equal to omega 1 of V, and omega 1 of V is in the image of T, in J of T, right? Okay. So this argument gives you projective stationarity as desired. Okay. So it's basically an absoluteness argument plus pulling back. So you force over V to get this capital G. You take the generic alpha power, then over M by absoluteness, you get that you get an element of the image of this curly S, which has the property that its intersection with the shifted up omega 1 is exactly the omega 1 of V, and therefore is an element of J of T, and then you pull back that statement and you get that over V you have the required substructure of H theta. Okay. Okay. So this is one direction, and the other, in order to show the other direction, let me just keep the statement of the theorem and erase this proof. Which seems to take a long time. I don't know why. The eraser doesn't work very well. Okay. So again, a sketch of the other direction, and you're welcome to fill in the details. So let's suppose this is not true. So we are assuming that the set curly S is stationary now, and we want to see that ns omega 1 is precipitous. So let's assume that it's not precipitous. So let's deny. Okay, so if that's not true, then there is a, then there is a generic, so that the over V, so that the generic alpha power is ill-founded. And if that's true by the forcing theorem, there would be a condition, so a positive set, so a stationary set which forces that it's ill-founded, right? So we have a T stationary, so that's the weird notation for stationary sets, so that T forces over V when forcing with the positive sets of the non-stationary ideal, that the generic alpha power of V by G, so the canonical name for the generic G is G dot, that this is not well-founded. Okay. Okay, but now we may take, now we have projective stationarity, right? Now you have your T and everything. So what you're going to do is simply you pick a theta big enough so that H theta can see everything, and you take a substructure X of H theta countable, so that what's written, so that this capital X is in curly S, and also X intersect omega 1 is in your given set T. Okay, so in other words, if you collapse, you will get an elementary embedding which has critical point alpha, and alpha is in T. And we may also throw in T into the range. So there is a T bar, which is the pre-image of T, so that, so in other words, alpha is in J of T bar. Okay, we want to pick it in such a way that X is also in curly S, so that when we derive from J a measure on the power set of alpha in the sense of M, that this measure is actually generic for M's version of the positive sets of the non-stationary ideal. Okay, so we may derive from J a little g, like in the definition of curly S, which is generic over M. And then this statement over here, that alpha is in J of T bar, means that T bar is actually in the generic. So T bar is in G. Okay, now upstairs, T was supposed to force that the generic alpha power of V by G dot is not well-founded. So just by elementarity downstairs, I picked theta big enough. So by elementarity downstairs, T bar forces over M that the alpha power of V, which is M, G dot, is not well-founded. Okay, but little g is a generic which has T bar in it, and the alpha power of, because G is derived from J, the generic alpha power of M by G may be re-embedded into H theta. Where do I have space to write it? Right, the picture is we have M, it's mapped into H theta by J. Little g was derived from J, and therefore the generic alpha power of M by G may be re-embedded into H theta, and everything commutes. Okay, but then that contradicts the fact that T bar forces that the generic alpha power is ill-founded, is not well-founded. Because if you embed something into a well-founded structure, in this case, if you embed the alpha power of m by g into h theta, then the alpha power of m by g is well-founded. Okay, so that's a contradiction. Okay, so we proved the equivalence of these two things, and as we pointed out yesterday, a consequence of this is kind of you can prove it kind of combinatorially, but this also now gives you an elegant proof of the fact that if the non-stationary ideal on omega 1 is saturated, then it is precipitous, because saturatedness corresponded to that every substructure has this property of self-genericity, and here precipitousness corresponds to that this curly S is projective stationary, and every club is, or every, if that's true for every substructure, then it's certainly, the collection of all the substructures is certainly projective stationary. Okay, so the consequence if n is omega 1, I don't know why I cannot write up here, so let me start. The corollary, n is omega 1 saturated, implies n is omega 1 precipitous. Okay, now as we go along, let's briefly discuss how to get n as saturated or n as precipitous. Before we discussed saturated and precipitous ideals, we discussed measurable cardinals, and there is a tight connection between precipitous ideals and measurable cardinals. So how do you obtain models in which, let's say, the non-stationary ideal on omega 1 is saturated or precipitous? Okay, the answer is that if you start out with a measurable cardinal and you first collapse the measurable cardinal by a Levy collapse to become omega 1 in the extension, then in that extension you have a precipitous ideal, and then you can work a little bit harder and shoot clubs through stationary sets which are in the ideal, and you keep going, and then you get a final extension where it's actually the non-stationary, where you turn kind of that ideal into the non-stationary ideal. Okay, so using a measurable cardinal, you can force and turn the measurable cardinal into omega 1 and make the non-stationary ideal on omega 1 precipitous. But this argument does not give that the non-stationary ideal on omega 1 is saturated, because that's a much stronger principle. In order for the non-stationary ideal on omega 1 to be saturated, you need to start with a wooden cardinal. And then there is an argument by Schindler, a forcing construction, a revised countable support iteration of semi-proper forcings, where you keep sealing anti-chains. We saw what that means to seal an anti-chain. So you keep doing that, and in the generic extension, the wooden cardinal becomes Aleph 2, and you have the fact that the non-stationary ideal on omega 1 is saturated in the extension. It's also true that Martin's maximum implies that the non-stationary ideal on omega 1 is saturated. I think this is in the original Foreman, Magidor, Schindler paper on where they introduce Martin's maximum. So in an ideal world, this is a theorem which we should also prove, but because of lack of time, I won't do it. It's a nice argument, and I invite you to go to the paper and read it. It's not difficult. Okay, and this kind of, unfortunately, it's kind of important for what we are going to do, but we cannot do everything. Okay. So unless there is a question to what we did so far, so we discussed saturated and precipitous ideals, we saw a connection, we saw characterizations. Is there a question on that at this point? So I want to move on and talk about the next topic, which was generic iterability. Which is a key concept when you actually define the ℙmax forcing, which is the forcing which you need in order to formulate Woodin's axiom star without generic iterability, without knowing what generic iterability is and without knowing how to get generically iterable structures. There is no way you're going to understand the ℙmax forcing. So what is generic iterability, right, of V? So we are going to prove it. So let's assume let's just work on ℙ1, but it's really not relevant. But this is the spot where in what follows we are going to work on. So it doesn't matter. Okay. So assume I is a precipitous normal uniform ideal on ℙ1. So that means, okay, now let's suppose, let's work in a forcing extension where we make some, you make your favorite uncountable cardinal countable. So let's work in V, call omega theta. In that extension, theta plus will be the new ℙ1, and there will be a lot of generics, right? There is, for instance, a generic for, because you choose theta big enough, there will be a generic for forcing with the positive sets of that ideal, and so on. Okay, so we work just in an external world to V, which one in particular it is, doesn't really matter. So there we may define the generic alter power. So let's suppose we pick, G, which now we call J0, and we call Vm because we're going to start iterating, V generic for the non-stationary ideal for the positive sets, right? So we get a generic alter power of M0 by G0. Okay, and you get this elementary embedding, which we call J, J01. This we call M1. It's a fully elementary embedding with critical point ℙ1 of V. Okay. So by elementarity, M1 will think that the image of the non-stationary ideal of ℙ1, which is just the non-stationary ideal on ℙ1 from the point of view of M1, is again precipitous. And therefore, if you pick another G1, which is now M1 generic for the non-stationary ideal on ℙ1 from the point of view of M1, this alter power will again be well-founded. So you call it M2, and then you can just keep going, right? So we do exactly the same as we did before with V in the presence of a measurable cardinal. We keep taking alter powers, but this time, in order to take the alter power, you first have to force over the given model, because the filter doesn't exist. It doesn't even exist in V. It's completely external in some sense. Okay, so we have to go to this first kind of master forcing extension V, call omega theta, in order to have a world where we can make choices on the generics. It's also important to point out that such iterations are in no way unique. You know, there are there are tons of choices for G0, and then there are tons of choices for G1, and so on and so on. There are kind of perfectly many choices you can make in the first step, and then again perfectly many choices in the second step, and so on. Okay, so they are not unique, so there is a whole array of such possible generic iterations. But in any event, if you do that, you can also pass through the limit stages by saying, again, as before, I want to define m omega as the direct limit, so that's the least model, so that everything in that model has a pre-image somewhere and the whole diagram commutes. And under the hypothesis that m omega is well-founded, again by elementarity, you can pick, right, this is now under the hypothesis that m omega is well-founded, you may pick a g omega, m omega generic for the version of the non-stationary ideal of m omega, and you just keep going. If m omega is well-founded, then m omega plus 1 is also well-founded by elementarity, because the non-stationary ideal from the point of view of m omega is precipitous. Okay, so successor steps are no problem at all. Okay, so now let's prove that you don't run into a problem at limit stages. That's an actual theorem, and it's a variant of the argument we saw that V is iterable by a measurable cardinal. And that's then the generic iterability of V. Okay, theorem.
Excuse me. How do you pick G1? You collapse another cardinal again?
Well, I said, you know, I was very vague about what theta should be. Just I don't know. You know, at the very outset of such a construction, you collapse theta. Let's say theta is, I don't know, aleph 15 or something like that. Okay, some big cardinal.
Right. This is for the first step.
Yeah, but you know the yes, but no. So you start at what's going on? Okay. So here we have V, right? So there is omega 1. So in the first step, you pick this generic G0, you get M1. And now your new, you know, everything is still small. So everything, so this takes place in V called omega theta. So theta is big enough. But then, you know, the relevant part, all I want is that, I guess I always need that the power set of omega 1, for instance, for the first step, what do I need in order to be able to pick a generic, right? I need
for the first step, I think it's fine, because h theta becomes of size countable in M1, right? You can find the generic for over this countable set for non-stationary ideal. But in M1 non-stationary ideal, at omega 1 is big.
Well, but I just picked theta big enough. You know, I'm not saying I can do this forever. I can only do it as long as you know, what do I need in order to pick? You know, I want to be able to enumerate the dense sets, let's say in order type omega, right? So right. I need to be, for the first step, I need to be in a world that the power set of, what is it? 2 to the, okay, I guess 2 to the aleph 1 should be countable. Is that true?
Yes.
What is the size of a typical subset of, yeah, okay, something like that. Okay, so if that is countable, okay, but then you may compute. Okay, so for the second step, I would need that the 2 to the aleph 1 of M1 is still countable. Okay, but you can compute, you can, you know, you can compute what that is, right? So you can do this as long as there is nothing deep here, right?
Okay.
There is nothing deep in what I'm saying. I'm just saying if theta is big enough, I mean, if theta is big enough that for a while all the 2 to the 2 to the aleph ones of the iterates will always be countable, and then we will have no problems in finding generics. That's all I'm saying. Okay.
Okay.
If you want, for instance, without thinking deeply, for instance, if theta were an inaccessible cardinal and we collapse everything below theta, so theta becomes the omega 1, right? Then certainly you can do that theta many steps. Do you agree?
I think. Okay, we can continue. Okay, thanks.
Okay. So in that part, there is nothing deep really going on. Okay. Okay. Okay, so let's prove. So if I is a precipitous normal uniform ideal on omega 1, and there is nothing special about omega 1 here, then V is generically iterable via, let me just write via I plus and its images. I didn't write down the formal definition of generically iterable. Generically iterable means whenever you pass to an extension like V call omega theta, and as long as you can pick generics for the process you're starting, then at limit stages you never run into ill-founded structures. Okay. So no matter how you pick the generics as you go along, at limit stages you're never going to run into an ill-founded structure. We discussed it by elementarity. At successor stages you're okay anyway because of the precipitousness of the ideal. And that's the very same argument we saw before for the iterability. That's a variant of the argument for the iterability of V via a measure. Via a given measure and its images, and we went through this argument via a measure in V and its images. So what you do is, so let me draw a picture, and then I invite you to fill out the details. So let's deny, okay? Let's suppose this is not the case. So what do we have? So we may start out with V, and there is this least limit ordinal lambda, so that if you do an iteration of length lambda up to and not including lambda, all the models are well founded, but then all of a sudden M lambda is ill-founded, is not well founded. Okay? So as before, we may argue then there is an alpha. As before, if M lambda is ill-founded, is not well-founded, then there is a strictly descending sequences of what M lambda things are all ordinals, and then you may pick an alpha in V, so that the image of alpha, if you shoot it up to M lambda, it starts a descending sequence of ordinals, right? So you have the image here, which you call A0. So the map from here to here, let's say, is J0 lambda. This is J0 lambda of alpha, and then it starts a descending sequence. Okay. Okay, and what else? So where does this whole process take place? Well, this takes place in some V call omega theta, right? So if what we are trying to prove is false, then there is a theta. So that in V call omega theta, there is a lambda and there is an alpha, so that this whole picture exists. Okay, and then what you do is you minimize the triple, right? You look at the triple theta, lambda, alpha, you look at the lexicographically least such triple, so that in V call omega theta, there is this iteration, the generic iteration of V producing m lambda, so that alpha, if you shoot it up to m lambda, starts in, so that below this image there is a strictly decreasing sequence of ordinals. Okay, and then you repeat the same way. Okay, so but there is a twist here, because there is an absoluteness argument which is also needed. Okay, so there will be an intermediate m. So m lambda is a direct limit. So every point in m lambda comes from somewhere. So there will be an m gamma which has a pre-image of alpha 1. So there is an alpha 1 bar here, and there is also an alpha 0 bar here. Okay. Okay, so now before, when we showed the iterability of V, we said that every model like m gamma can see the tail end of the iteration, for instance, the iteration leading from m gamma to m lambda. That's not true here. Not even V can see this iteration, because it's completely external. The generics are not in V. Okay, but a model which is external to m gamma can see it. I mean, this iteration from m gamma to m lambda exists somewhere, namely in the collapse extension of V. And then there is an absoluteness argument. This is the new feature of this argument. There is an absoluteness argument saying that if starting out with m gamma, you have an iteration like that producing this picture, then over a forcing extension of m gamma, there is also such a picture. Okay. So it turns out that you can say that over m gamma, if you force with omega, with a collapse of omega to, with theta to omega, so by absoluteness over this model, you can see that there is alpha bar 1, which sits below alpha bar 0, so that if you look at the generic iteration and you look at the image of alpha bar 1 and move it up to m lambda, then this starts a descending sequence of ordinals over there. Okay, and this now is a first order statement which is true over m gamma, and you can pull it back to V. So over V, there must actually be something below alpha, which in some collapse extension starts a descending sequence. Okay, so if you organize it in the right way, then you get a contradiction to the minimality of the chosen triple. So the new twist is that the iterations cannot be seen in the respective models. So no model can see the sequence of the further iterations. It doesn't even see the first alpha power, but then there is an absoluteness argument which comes in. Okay, but it's a variant of the argument before. Okay. So for now, this ends the discussion of iterability and generic iterability. And now I want to turn about discussing effective counterexamples to the continuum hypothesis and introduce the relevant concepts. We have a bit more than half an hour before the break. Okay. So effective counterexamples to the continuum hypothesis. Or sometimes you say definable counterexamples to the continuum hypothesis. So there is a paper by Foreman and Magador with a similar title, I think, definable counterexamples to the continuum hypothesis, where the question was discussed to which extent it's consistent in the presence of large cardinals to have such counterexamples. And this was before Hugh Woodin had verified that actually from Martin's maximum, it follows that there are such counterexamples. And there are still a lot of open questions in this area. So for instance, you can ask to which extent can the continuum hypothesis fail in an effective way. Okay, so we already know, we discussed a little bit of that, right? So in the presence of Martin's maximum, we know that, let's write it that way, we already know that under Martin's maximum, and we actually proved everything of that, it's true that the continuum is the same as 2 to the LF1. This was this proof that under Martin's axiom sub omega 1, 2 to the LF0 has the same size as 2 to the LF1 because every subset of every subset of omega 1 is coded by a subset of omega modulo 1 fixed sequence of pairwise almost disjoint sets, subsets of omega, and this is equal to LF2, and therefore a way to write this down is that there is a function f from 2 to the LF0 or from the reals onto omega 2. Now, if you have such a function, we may look at a binary relation on the reals, and then you are in descriptive set theory, right? So you may look at the pairs x and y from R square, so that f of x is less than or equal to f of y. So this is a subset of R cross R. And you may look at what is the least possible, or what are possible levels of definability of that thing. Okay, let me call this relation R sub f. You know, how easily can such an R sub f be definable? From R sub f, you can also read f by just taking, looking at the ranks of x's under this relation. So you can read off little f from R sub little f. That's no problem. Okay, so what are levels of possible definability? So one crude question would be, can you have such an R sub f? When I say such an R sub f, what I mean is, can I have a function which is surjective from the reals onto omega 1 so that the derived R sub f has the following property, namely that it's in L of R, for instance, where L of R is the least transitive model of ZF, which contains all the reals and all the ordinals as a subclass. Okay, so it's kind of the least inner model which contains all the reals. So in contrast to the constructible universe, which need not contain all the reals, and in fact in the presence of large cardinals does not contain all the reals, it has only countably many reals, the constructible universe. Here you build a model where you throw in all of the reals at the bottom and then you do the constructive closure. So you get the least transitive model of ZF, which contains all the reals. In the presence of large cardinals, you can actually prove consistently L of R is a model of choice. For instance, if you do this construction inside the constructible universe, you just get the constructible universe back. But in the presence of large cardinals, where the constructible universe is small, if you do the construction of L of R, you get a model which is a model of ZF, but not of choice. Okay, because it satisfies determinacy. We will have to talk a little bit about determinacy tomorrow. At least we need one consequence of determinacy when we discuss the ℙmax forcing. Okay, So you can ask if that is possible, but there is a more strict, there is an even more demanding variant, or even can in the presence of large cardinals, or what's interesting for us under Martin's maximum, such an R sub f be projective. So what does projective mean? So there was a question, I think, yesterday, and now finally there will be the answer. So a set A, one way to define it is that you say that a set R, let's say a subset of R to the n is projective. What you want to say is that it's definable over H sub omega 1 or HC from parameters. If R is definable with parameters over the structure HC, so this is the hereditarily countable sets. This is not the usual definition of a projective set. But let me point out that H sub omega 1, the hereditarily countable sets, because you put in all the reals into L of R and every element of HC is coded by a real, the HC of L of R is the same as the true HC. So if something is definable over the HC of V, it is certainly an element of L of R. So if you have an R sub F which is projective, then this R sub F is certainly in an element of L of R. So this is why this question we have on this board now is more difficult than the previous question. Okay, the usual definition of projective is a little bit different. Maybe I just say it in words because we don't really make use of it. Usually what you say is you start out with open and closed sets. So you define what an open and closed set of R is in the usual fashion, starting with intervals or with open sets, which generate the usual topology on the reals. So you start out with the open sets, and then you keep and then you say that a set is projective if you can define it by in the way, okay, let me write it down. Equivalently, R is projective if and only if you can write that X vector, so R is a subset of R to the n, X vector is an element of R, if and only if, and then you have a block of quantifiers which range over reals. So for instance, there is a real x0, so that for all reals x1, so you have a finite sequence of alternating quantifiers with last quantifier q, so that X vector x0 up through xk is an element of C, and C is a closed or open set, or if you really work with the reals, we should say that C is a Borel set here. Okay, if you can write it down in that fashion. Okay, you may also start with a universal quantifier, and the number of quantifiers doesn't matter as long as it's, of course, finite, because it has to be a formula. So that is actually equivalent, and there is a level-by-level correspondence between these two things. But for our purposes, it's okay to try and remember this definition. Okay. So these are projective sets. What's also relevant for us is not only being definable over h omega 1, but a structure which is of particular importance in the context of forcing axioms, and also even in the presence of bounded forcing axioms, is the structure h omega 2. So h omega 2 is, h theta is just a collection of things which are hereditarily of size less than theta. So this is the collection of things. Okay, I give up to write here. Let's write it here. Oops. Okay. So this is a very important object. So we say that a set, I just want to give an example for the number 2, but of course it doesn't have anything to do with 2. You can do it for all, and you can do it for sigma as well as for pi. But for us important is a formula is pi, the formula phi is pi 2 over h omega 2 if it is equivalent, let's say in ZFZ, to a formula of the form for all a, okay, being an element of h omega 2, there is a b so that psi a and b holds, and the formula is allowed to have some free variables, so they show up here, where c is sigma 0. Sigma 0 means that all the quantifiers are bounded. Okay, so the formula is allowed to have parameters, and okay, this is a particular important class of formulas for us. Okay, we may also define, for instance, sigma 2. Sigma would mean you start out with an existential quantifier. You can also define pi n and sigma n. Then the n just gives the number of alternating quantifiers, and in the pi case you start out with a universal quantifier. In the sigma case you start out with a, what did I say? In the pi case you start out with a universal quantifier. In the sigma case you start out with an existential quantifier. So now what we want to do is, why did I define this particular class? Because this is important for our context, because it turns out that Martin's maximum is sort of complete with respect to natural pi 2 over h omega 2 statements. Okay, and there is actually a theorem which one can prove, which was originally proved by Hugh Woodin for the context, in the context of the star axiom, who proved that the theory ZFZ plus star is omega complete with respect to omega consistent pi 2 over h omega 2 statements. But now we know that star actually follows from Martin's maximum by my result with David S. Pro, so MM also is complete in that sense. So this is an important class an important complexity class of formulae. So let me give some examples. Important examples of such formulae. So the first example I want to give is the fact that U2 is equal to omega 2 of V. And I didn't tell you yet what U2 is, and I want to define what U2 is. Okay, so what is U2? Okay, so there is a brief discussion. Let's go back to the discussion of sharps for reals. We said a little bit about that yesterday. So let X be your favorite real, or let's say a subset of omega. So X sharp, we said, is the statement, the existence of X sharp is the statement that there is a non-trivial elementary embedding from L of X into L of X, but there was a but it was mentioned that there is an equivalent formulation in terms of the existence of mice. Namely, we said that this is equivalent to saying that there is an iterable structure of the form L tau X together with a predicate which externally is a measure on the largest cardinal of L tau of X. So the construction was that if you have an elementary embedding from L of X to L of X, it has critical point kappa, and then you derive a measure on the power set of kappa on all the sets which are subsets of kappa and exist in L of X. So this is your U. You use the embedding to get this U. This U is not an element of L of X. You cut off the structure L of X at the successor of L of X of kappa. And an argument which we did not give shows that this structure is iterable in the sense that, I told you how to make sense of the iteration. So U is external, but it doesn't matter. When you take the alter power of L tau X by U, you get the new universe, but we may also break up U into pieces which are elements of L tau X and then move up the individual pieces and put them back together, and then you get a new version of U and you can keep going. And there is a theorem which shows that this never leads to an ill-founded structure. And then once you have that characterization, it's very easy to see that I mentioned it yesterday that there are other characterizations of the existence of zero sharp, that there is a proper class of what's called silver indiscernibles for this context, or then X indiscernibles. A proper class C, which is also actually a club. So what is a class of X indiscernibles? So that means that whenever you have a vector kappa and another vector lambda from C, so what does that mean? That the individual points are all in C, and what I want is that the order of the elements of the K vector is the same as the order of the elements of the lambda vector. For instance, think of kappa vector as a strictly increasing sequence from C. Think of lambda as a strictly increasing sequence from C. Then you will have that for every formula phi, L of X is a model of phi at kappa vector if and only if L of X is a model of phi lambda vector. This is what it means for C to be a class of indiscernibles, of X indiscernibles. And you can pick the x indiscernibles in a way that this family is actually generating. So actually every element of L of x is the result of applying a Skolem term of L of x to a finite sequence of indiscernibles. I forgot to stress that kappa vector and lambda vector is always finite. Okay, so this is the concept of indiscernibles, and it's not hard to see that if you have an iterable structure L tau x, comma u as above, then you iterate the structure out of the universe. So you look at an iteration of that structure of length the ordinals, then the critical points of the sequence of the critical points of the measures you generate of the images of U is a class of x indiscernibles. So this shows the direction from the fact that you have such an iterable structure to the existence of indiscernibles. And once you have indiscernibles, it's easy to derive a non-trivial elementary embedding for L of x. So all these things are actually equivalent. Okay, so this is the theory of indiscernibles, which goes back to Jack Silver in his thesis. So once you have that, you may define what U2 is. So we may define, you may look at, you have this proper class C of X indiscernibles, and I said that it's actually a club. So if you look at all the reals under the hypothesis that every reel has a sharp, you have all these proper classes which are clubs. So you may simply intersect the collection of these classes of indiscernibles. So the intersection of set many clubs is a club, and the elements of the intersections of all these clubs, they are called uniform indiscernibles. So you may wonder what is, for instance, the least uniform indiscernible. No countable ordinal can be a uniform indiscernible, because if, for instance, the real x codes a surjection from omega onto alpha, then certainly alpha cannot be an L of x indiscernible, an x indiscernible. And on the other hand, omega 1 is always an x indiscernible. So the least uniform indiscernible is omega 1, and then the question about U2 is what is the next uniform indiscernible. You can define, okay, let me write that on the next. So if let x sharp exist for every real x, so there is a class, and it's actually unique, C sub x of generating x indiscernible, generating meaning that every element of L of x is the result of applying a Skolem function of L of x to a finite vector of x indiscernibles. Okay, and then you say that the class of uniform indiscernibles for reals is just equal to the intersection of all the c-x's where x is a real. So this is again club. So these guys are all club. So this will be a club. The minimum of C, as we just discussed, is omega 1. And this is the only point I'm familiar with, or I know of, where you start indexing something with 1 instead of 0. Namely, you say that we let ui I less than the ordinals, but you take out 0. So this is an I, be the monotone. enumeration of C. So by the line before, we have that U1 is equal to omega 1. This is probably why you start counting with 1. And every cardinal is an X indiscernible for every real X. And therefore, the second uniform indiscernible U2 is less than or equal to omega 2. So this is in ZFZ if sharps exist for all reals. And then the question is, what is the true size of U2? And the statement I just wrote down says that U2 is equal to omega 2. Okay, so why is that pi 2 over h omega 2? Maybe this is something we can do before the break. We have almost 10 minutes. So now let's go back to the statement. To the statement U2 is LF2. Okay, so what does that mean? Okay, there is one thing which so what is the easiest way to see that this is a pi 2 statement? The easiest way to see that is, let's work with another characterization of U2. So U2 is the second uniform indiscernible. But you can actually, it's very easy, and I invite you to think about it. It's very easy to show that it's also in the presence. We are working here under the hypothesis that X sharp exists for all the reals X, I. Okay, so then it's also the supremum of omega 1. So this is the omega 1 of V, and you look at the cardinal successor of omega 1 of V in L of X for a real X. So these two things are the same. It's very easy to see that the supremum has a bound, namely being the second uniform indiscernible, but the other direction is true also. So that's true in the presence of sharps. And then it's easy to see that U2 being L of 2 is pi 2 over h omega 2, so U2 as a statement. Because what do you have to say? You have to say that for every alpha less than omega 2, there is a real X, so that omega 1 of V plus of L of X is at least alpha. And this you can express by another existential quantifier which ranges over h omega 2. I mean, the two quantifiers which I wrote down here, they range over objects in h omega 2, right? The alpha is less than omega 2, reals are also in h omega 2. Okay, so I can write down this equivalently as saying that there is a structure, that there is some, I just have to say, okay, I have to compute omega 1 of V, and I have to then compute something which is at least the omega 1 of V plus of L of X. So a way to do that is I can say there is a transitive structure I mean, I can avoid using kind of omega 1 as a, so there is a transitive structure N. Okay, I want to say there is an object which will become the omega 1 of V. or something which is at least as big. So there is a beta, there is a transitive structure n of height beta, such that this structure doesn't have any, that everything is countable in n. And then I can say, and there is an L sub gamma of x, where gamma is now bigger than beta, so that alpha is less than or equal to beta plus of that structure. I should say. So this is just one way to spell out what I want to have. So for every alpha less than omega 2, there is a real, there is a beta, there is this transitive structure n which witnesses that beta is, well, big enough, and this alpha is then smaller or equal to beta plus of a version of L of x. So this is a way to spell it out. So it shows that the statement U2 is omega 2 can be phrased in the pi 1 over h omega 2 fashion, and it's the first instance of showing that there are important statements of that kind. The other thing, we have a few minutes, so I kind of leave it as an exercise. So under the hypothesis that U2 is omega 2, remember that we always assume that every real has a sharp, which by the way follows from Martin's maximum. What we may do is we may define the following function. We may define f from the reals, or if you want, identify the reals with the power set of omega onto omega 2, and we just say that we map an x to omega 1 plus of L of x. Because U2 is omega 2, this is cofinal. Okay, and then we may wonder, and then now I'm going for projective and for the effective counterexample, right? So let's look at the set of pairs x and y from the reals, so that f of x is less than or equal to f of y. Okay, and that's I claim that that's a projective set. So that may be rephrased in a way. I claim that this is projective and maybe actually I want to say a few more words on that, and maybe we then should first make a break, and I say a little bit more on that after the break. If you want to have something to do in the break, you can think a little bit about why that should be projective. Okay, let's make a brief break.
Great. Start the second half after today's lectures.
Okay, great. So we simply continue where we ended before the break. So before the break, we defined what it means that U2 is omega 2. We also said, right, so U2 being omega 2 means that omega 2 is the second uniform indiscernible. And if you can phrase it in a way that you don't have to talk about indiscernibles, but then the characterization only makes sense in the presence of sharps. So the statement says the same as omega 2 is the supremum of all the omega 1 of v pluses of L of x, where x is a real. By the way, it's very important that I write omega 1 of v here and not omega 1 of L of x or something. Because if I wrote omega 1 of L of x, then this thing would just be omega 2 of L of x, and this is always countable if x sharp exists. And then the supremum would just be omega 1 is the wrong thing. So it's important to write it down exactly in that way. And then I promise that after the break, and that's what we are going to do now, I will show that this relation, which before we called R sub f, the set of all pairs x comma y, so that f of x is less than or equal to f of y, that this is actually projective. I did not introduce the projective hierarchy, but for those of you who are interested, one can prove that this is actually a delta 1,3 relation. But let's do that, okay? I want a little bit more space in order to do the argument. So let me repeat by saying that, okay, so we define so for an x in here, you say it goes to omega 1 of v plus of L of x, and you look at the relation R sub f. So in other words, we are interested how complex, what's the complexity of the relation omega 1 plus, omega 1 of v plus in the sense of L of x is less than or equal to omega 1 v plus of L of y. So we have to write that down in a way which is as simple as possible. So it turns out that one way we can do it is we go back to mice. Okay, we can say, I claim that this is equivalent to having that there is another real y, and there is one of these iterable mice, like we discussed in the context of the definition of in this case, Z sharp. So there is an L tau Z U, an iterable mouse like we discussed before, so that L of tau and Z, I mean, you can think of that real actually to be such that, for instance, X and Y are both Turing reducible to Z, something like that. That's the canonical way to think of it. And what we want is that L of tau on Z, U thinks, okay, so this is a measure on kappa, the largest cardinal of L tau of Z, and then what you want to say is that L of tau and Z thinks that kappa plus of L of X is less than or equal to kappa plus of L of Y. Well, from the point of view of that model, okay? So if X and Y are coded into Z, then, you know, L sub tau of Z can talk about its own version of L of X and its own version of L of Y, and then the statement makes sense. Okay, so this is the statement. First thing, why is this an equivalence? Well, if, you know, to go from left to right, well, if you have a, or rather, I think I'm going from right to left. If you have the right-hand side statement, right? So you have this little structure, L tau and Z. So here is tau, here is kappa. So here is the kappa plus of L of X. What I claim is that if I have an iterable structure like L tau Z and U, and it thinks that something is the kappa plus of L of x of that structure, you know, L sub tau of z does not contain all of L of x, because L of x is a proper class and tau is just an ordinal. So in general, L sub tau of z is mistaken about the cardinal successor of kappa of L of x, because above tau there might be new subsets of kappa showing up. But in this particular situation where L tau z comma u is an iterable structure, I claim that that's not the case. So I claim that the object which the structure thinks is the cardinal successor of kappa in its version of L of x is really the true cardinal successor. So why is that true? I can start iterating this structure, and this will give me an iteration like that. Okay, but it turns out that in this iteration, you know, now you have to do all the computations from the theory of mice, which in this simple case is really not very difficult. If you look at the further iterations, tau will actually be the cardinal of all the further iterates. This follows from the immutability of the structure. Okay, so tau later on in the iterates of that model L tau z of u, tau will actually be the cardinal successor, and then in the end it will actually be the cardinal successor of all of L of z. Okay, this is a general feature of these mice. Okay, but then just by elementarity, if L sub tau of z thinks that something is the cardinal successor of kappa of L of x, then this is really true, because there are no other subsets of kappa which show up later beyond tau. Okay, so what this little structure, which is again countable, thinks is the cardinal successor of kappa in L of x is really the true cardinal successor. Okay, and therefore we have actually the equivalence, right? So what these little structures think, as long as they are iterable, is really true about L of x, as far as the successors of kappa go. Okay, so this shows the equivalence, and now we have to take a look at what's the actual complexity. So we are saying there is this real, there is this structure, blah blah blah. So far this looks like sigma 1 over, right? I mean, all these structures which are involved here are countable, right? So we talk about a real z, we talk about a countable structure, L tau z u. We can take these structures as being countable by taking Skolemhal. So everything's countable here. Okay, so we are talking about, so far this looks like sigma 1 over hc, but it is not really, well, it's not really sigma 1, because we have to express iterability, and this brings in another universal quantifier. So you have to say there is a z, there is a structure L tau z of u such that blah blah blah, but also you want to say that L tau z of u is iterable, and this means that if you give me a countable, or if you give me an ordinal alpha, then the iteration of that thing of length alpha is okay. It never produces an ill-founded structure. So this is another universal quantifier, and you can show that this is equivalent to saying that for every countable alpha, the iteration of length alpha is okay. This is another Skolemhal argument. If there is any iteration of L tau z u of any length, which produces an ill-founded model, then there is one of countable length. And therefore, the complexity of what's written down there is sigma 2 over hc. So the complexity, I did not define sigma 2. Sigma 2 just means that block of existential quantifiers, block of universal quantifiers, and then something easy, or then sigma 0. Over h omega over hc. Okay, so I also briefly mentioned that there is a correspondence between being the level of definability over H omega over HC and the complexity in terms of the equivalent definition, how we wrote down what a projective set is. So sigma 2 over HC corresponds to sigma 1, 3. And we can also express the same thing as a pi 1, 3 statement, or if you want pi 2 over HC statement by quantifying over all Z's and all such models which are iterable. So you can also equivalently say for all Z, for all such iterable structures, if they can see X and Y, blah, 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 then blah, blah, blah. Okay, so in that fashion, the statement is delta 2 over HC, and that's the least possible you can do. Okay, so in any event, it turns out that this relation R sub F is projective, so it's very easy, and in particular, it's an L of R. Okay. So let me move on to discuss other statements of the same complexity, other important, and there are more. I only give you some examples. Important pi 2 over H omega 2 statements. Okay, what we saw is, we saw this statement, U2 is equal to omega 2. There is another statement, I think, introduced by Hugh Woodin, which is called admissible club guessing. What is the statement? It says that whenever you give me a club C, there is a thinner club D so that D is actually given by the admissibles below omega 1 relative to some given real. So there is a real X, so that D is the set of all countable X admissible. What is an X admissible? An X admissible is an ordinal tau, so that L sub tau of X is a model of the Kripke-Pladik set theory, which is a weak fragment of Z of Z. So for the purpose of this talk, you may actually think of, it would be an equivalent statement if you actually said that D is the set of all countable tau, so that L tau of X is a model of Z of Z. And actually, equivalently, you could also simply say that for every C, there is a thinner club D, so that the club D is an element of L of X. Okay, or just. So this is admissible club guessing, and it turns out that admissible club guessing implies U2 being L of 2. It can also be shown that by itself, you know, the statement that U2 is L of 2 only makes sense if you have sharps for reals. Admissible club guessing by itself implies that sharp for reals exist. Now there are two other statements which are important, namely phi AC and psi AC. And in the discussion of the ℙmax forcing, they are both very important. So they are both variants. Remember the way how we prove under MM that 2 to the Aleph 1 equals Aleph 2. It was a specific way of proving it. We showed that you know, you are given. You are giving the splitting of omega 1 into omega 1 many stationary sets in this particular way, the T sub i's, and then you have this other splitting of S omega 2 omega into omega many stationary sets, and then into omega 1 many sets, and then, you know, for an index set, you add this kind of reflection point. So there are somewhat more local statements of what we have. So we said that there is this reflection point, there are more local statements, and these phi and psi, they are local variants. Maybe I want to write down what it means, even if we won't have a chance to discussing it. At least I want to write down the statement psi AC, this one. So psi AC is the statement that whenever you have T and S, they are both subsets of omega-1 and they are both stationary and co-stationary. Then there is an eta. Okay, I need a little bit of more space, sorry. Let me erase that. Okay. So for all tau and S, they are subsets of omega-1, both stationary and co-stationary. There is an eta less than omega-2, such that you have that, so I should write it down more clearly, eta less than omega-2, so that you have that psi is an element of T. Basically what you want to do is you want to reduce T to S modulo a, how are they called, a canonical function, sorry. So F sub eta of psi is an S for all psi sub less than omega-1 on a okay, let me write down more clearly. There is a club such that for all psi in the club, this holds true. So what is this function? This is a canonical function. So how do you define f of eta? You pick your favorite g, which goes from omega-1 onto eta. And then you say that f eta of psi, where psi is a countable ordinal, is equal to the order type of G, the pointwise image of G at psi. Okay, so this is the canonical function corresponding to eta. Okay, and you have this equivalence, and if you look at things, this is a refinement, and also the phi AC up there is a refinement of the statement which we used in order to prove that 2 to the LF1 is LF2, and it will be relevant in the context of Pmax forcing to show that even the Pmax extension, to even show that the Pmax extension is a model of CFC. You verify, for instance, psi AC, and from that it follows. This is why you have this subscript AC here, because it's used to show that the axiom of choice holds in the Pmax extension of L of R. L of R is not a model of choice. Okay. So we have a bit more than an hour. What I wanted to do next is I wanted to give you an illustration of the, so there is this diagram here and you can fill in many more things. So it was known that star, which we did not yet introduce, implies all these things. And these are all pi 2 over h omega 2 statements. And nowadays we already also know that mm plus in fact implies star. So you have this picture that mm double plus implies all these statements, and there are other statements which before had only been known to follow from star, but had not known to follow from mm double plus. Okay, so what we're going to do now is we're discussing kind of fragments this diagram. So in the remaining time of today's talk and also tomorrow's talk, we kind of we stay in this diagram and we discuss aspects of this diagram. You could discuss this kind of diagram for days and days. Okay, so we want to discuss the following aspect. What I want to do now is I want to show or sketch a proof of the fact that admissible club guessing implies that U2 is omega 2. And then the next step, I want to show that just MM alone implies admissible club guessing, and therefore MM implies U2 equals LF2. There is a much simpler proof, as I said in the beginning today, to show that. If you just want to show that MM implies U2 is LF2, there is a much simpler proof, but we will do it in a more complicated way. And the more complicated way will then actually be the one which shows that MM double plus will also yield to a proof that MM double plus implies star. And I will try to do this in the remaining time. We will see how far we can get. Okay, so for now, I think this theorem is due to Fudan, who introduced admissible club guessing. So admissible club guessing. And we also assume, I wrote down that it implies sharps for reals. We are not going to prove it, but our context is that sharp for reals exists. So this implies that U2 is equal to omega 2. Okay, so let's try the proof. Just to illustrate, to warm up with all these statements and see that there are actually interrelation, that there are connections between these various statements. Okay, so what we're going to do is, what do we have to do, right? We have omega 1 up here. You give me an alpha, and I basically have to come up with a real x so that omega 1 plus of L of x is above alpha. Okay, so fix a bijection of alpha with omega 1. And let's take a tower of substructures. Xi, I less than or equal to omega 1. A tower of elementary substructures of some big h theta as usual, right? So okay, so we collapse. So as usual, the xi's are all supposed to be countable for an I less than omega 1. And it's a tower, so you just take unions at limits, and x omega 1 will then be of size LF1, right? So this is something I don't write down. This is supposed to be true. So we do the transitive collapse of xi, so I call it ni. Okay, so for a typical I, we have the following situation. So you have ni here, you have an elementary embedding from here to here. Okay, let's call, and also you want to throw in relevant objects into even x0, and I'm not going to write it down. For instance, f is supposed to be an element already of x0, right? Okay, so we have a pre-image of alpha in all these structures, which I call alpha I. So this goes to alpha. Okay. And by thinning out the tower of substructures, I can make sure that it's always the case that alpha I is less than the omega 1 of ni plus 1. So this is the omega 1, this guy. This is the omega 1 of ni. So the omega 1 of the next guy is bigger. And by thinning out the sequence, I can make sure that this is actually true. Okay, so I want to apply, so we want to deduce something from admissible club guessing. So what I'm doing now is I apply the admissible club guessing principle to this set of omega 1s of the ni's, and I also want to add the statement that I is actually omega 1 of n of I, which I can assume without loss of general. I mean, this is true on a club. Okay, I less than omega 1. So this is a club. So I have a club. And all I want is that D is an element of L of X. Okay. So now D is an element of L of X. So every element of L of X is generated from, is gotten by applying a Skolem term to generating indiscernibles. And I can enlarge X a little bit more in order to make sure that I actually don't need countable indiscernibles. And I also can replace, if necessary, X by X sharp in order to say that I actually don't need any indiscernibles which are strictly above omega 1. Okay, so we may assume that D is definable in L of X just from the parameter omega 1 of V. Okay, so let's fix some such definition. Okay, so if so we have that psi is in D if and only if L of X is a model of phi of psi, you have X and you have omega 1 of V. Okay. Okay. So if eta less than omega 1 of V is an X indiscernible, by indiscernibility you will get that psi is in D intersect eta if and only if L of X is a model of phi psi X eta. You know, omega 1 of V is an indiscernible, so you may you get all these kinds of, because of indiscernibility, the way we wrote it down, it easily seemed to imply that you get all kinds of embeddings from L of X into L of X by just shifting the indiscernibles. Everything in L of X is generated by applying a Skolem term to indiscernibles. So this gives, if you give me a shift of indiscernibles, this induces in a canonical fashion an elementary embedding from L of X into L of X so that restricted to the indiscernibles, this is actually the shift you gave me. And therefore we have this property. Was it a question or no? Okay, so if we, yeah, okay, can you try to keep in mind what we had on this board? So now I'm going to the next board. Right, so if you draw it as a picture, you have L of X here, you have L of X here, you have omega 1 here, you have D here. There is this shift that maps the indiscernible eta to omega 1, and here we have D intersect eta, and you have this picture, so this gets mapped to here. Okay, so this means that every X indiscernible, right? I mean, just by elementarity, omega 1 is a limit point of D because it's club, so D intersect eta has supremum eta, so every X indiscernible is a limit point of eta, of D. Okay, so let's see, what do we have now? We have that if psi is in D, which, by the way, implies that psi is equal to omega 1 of n sub psi, right? But it also implies psi in D implies that the next, this is just what I wrote above, the next X indiscernible, which is bigger than psi, is bigger than the omega 1 of n of psi plus 1, right? And therefore, because we thinned out this sequence in such a way that this thing, that a sub psi is actually smaller than that, so this is, it's bigger than a sub psi. Okay, so in other words, if psi is in D, then the next X indiscernible above psi is bigger than a sub psi, right? Okay, and now we have this observation, and now we pick another tower of countable substructures of V. So yi, so again, this is a tower of, so that yi is countable for every I less than omega 1. You take union and set limits. Okay, so what do we want? We have this X we chose before. So now what I want to do is I want to put X sharp into Y0 and also, well, F into Y0. I can put in anything I want. So if X sharp is in Y0, D is definable from X already. So in particular, the club D is an element of Y0. Okay. So now we have these two towers. We have a tower X, and we have a tower of X sub i's. We have a tower of Y sub i's. And of course, if you have two such towers, if you look at the intersections of the elements with omega 1, so on a club, that's the same, right? So there is a club E, and we may thin it out if necessary to say that it's a subset of D, such that yi intersect omega 1 is just equal to xi. This was the tower before for all I in E. Okay. So let's see. Okay, so this is where we are now. So let's look at what's happening. So let me now pick an element of E, of this thin club E. Okay. So let's look at what's going on. So we had our alpha up here, which you gave me. We have omega 1 here. We had alpha I here. We had the omega 1 of yeah. Okay, now we are looking at right. This is supposed to be M I, not the right. This is supposed to be the transitive collapse of yi, not of xi. Okay, but remember that alpha is in even y0 because the function, the bijection between omega 1 and alpha was in y0, so alpha is there. So alpha has a pre-image, and this is a This I now also call alpha I, but this is not a very good notation. It should be this guy. Okay. Okay. Now, from what we showed before, give me 1 second. I'm sorry. I'm sorry. Not only that, what I wrote down on the previous slide, I meant to write down something different. I wrote down that on a club, yi intersect omega 1 is equal to xi intersect omega 1. That's not what I want. What I want is I want to have it actually for alpha, and that's also possible, right? So alpha is bigger than omega 1. Sorry. So the correction. So E is supposed to be the places, so have E subset of D club such that for all I in E, yi intersect alpha is actually equal to xi intersect alpha. Right, in both cases, alpha is a subset of the model x omega 1 as well as of the model y omega 1. So on a club, you will have that yi intersect alpha is equal to xi intersect alpha. That's important. So what I called alpha I star here is actually then the same as alpha I. Okay, here we go. Okay, so if you look at the map, which sends mi into basically v or h theta, then the pre-image of alpha is also the old, what was called alpha I before. It's the pre-image of alpha under the collapse of also xi. Okay, and now we have, by what we showed before, that mi thinks that the next x indiscernible above I is bigger than alpha I, okay? And therefore, by elementarity, we will have that upstairs, the next x indiscernible above omega 1 is bigger than alpha. Okay, and that now we proved that omega 2 is equal to U2. Okay, so this was the argument that admissible club guessing implies that U2 is omega 2, and this statement U2 is omega 2, I decided is one which we want to try to derive from Martin's maximum by this more complicated way. So now it is 5 minutes to 11. We have like 15 minutes. Is that true? Or am I confused now? I think so. Otherwise, just stop me. I mean, we sort of have 3/4 of an hour, right? Is it?
We have more than 50 minutes, I guess.
Yeah. I think we have less than 1 hour.
Yeah, less than 1 hour. Yeah. I was just wondering that I don't get confused again. Okay, so let me see. Where are we? Okay, so now you know, remember this diagram, right? So plus plus, we introduced that statement. We did not introduce star. I'm going to do it tomorrow. But as a matter of fact, this thing implies admissible club guessing, and then it implies that U2 is LF2, and it implies all these other things. So there were other things here in the diagram which are not relevant for us at this very moment. So what I want to do now is I want to show you a proof of that, and therefore a proof of U2 equals omega 2 from Martin's maximum. But as I said, I do it in a way that it is inspired by the proof with David Aspro to give star. Okay, and of course we are not able to give the full proof, but I will try to give aspects of the proof today. Okay, so okay, so you want to do admissible club guessing. Okay, I want to reduce showing admissible club guessing to something where we have a chance to actually force it. So look, admissible club guessing. So we are given a club in omega 1, a club. Now suppose I can do the following. Okay. Yeah, actually, it's hard to see why we make it so complicated, but okay. So maybe I should start out by giving the easier proof actually. So look at h theta. H theta. Where theta is big enough. I guess for our purposes, it could actually, we could just pick theta to be omega 2. Okay. Why don't we do that? Okay, I want to equip it with the epsilon relation, and there is a predicate for the non-stationary ideal here. Okay. So I mentioned that under Martin's maximum, the non-stationary ideal on omega 1 is saturated. We did not prove that, unfortunately. So, but we saw the equivalence to the fact that the non-stationary ideal being saturated is equivalent to that if you take any countable substructure, if you derive a measure from the embedding, then that measure is actually generic for the collapse of the countable substructure. Okay. Now, what we want to do is the following. So we have this club, so throw in the club into a tower, into the least model from a tower of substructures, right? So we let again xi, I less than or equal to omega 1, be a tower of substructures. So by tower of substructures, again, I mean a tower of substructures of some h theta, theta big. And what I want is that C is in the first model x0, all the xi's for I less than omega 1 are supposed to be countable, and xi then will have size LF1. Okay? So in particular, C is in x0. Okay? So if Ni as before, in much the same way as before, is the transitive collapse of xi, then I have two things. And let me call alpha I the omega 1 of Ni which is, so there is a map J I omega 1 here. This is J I omega 1 to the minus 1 of omega 1. Okay. So I have two things. First of all, because C is in X0 already, there is always a pre-image. And what is the pre-image of C? It is just C intersect alpha 1, right? So C intersect, intersect alpha I. So C intersect alpha I is the same as the pre-image of C. In other words, J I omega 1 of this guy is just C. Okay. So all these alpha i's as before, they are limit points of C. Okay. And also, the other thing I have is that I can use the map J sub I omega 1 to derive a measure. So actually, I'm not really that much interested in this tower. I will form a tower by picking generics. So let's back up again. Okay. So I want to choose a particular such tower. Okay. So what is this particular tower? I start out by taking an X0, a countable substructure of H theta, which has C in it. And I think automatically the structure, just because it's very nicely definable, H omega 2 epsilon ns omega 1. The structure will also be in X0, okay? So I call this N0. Okay, we may define G0 as, so this is the omega 1 of N0. There was C here. There is the pre-image C intersect alpha 0, which goes to C. We may define G0 as the derived measure. So this is all the x's which are in the power set of alpha 0 intersect this structure, so that alpha 0, which is the omega 1, is an element of, so the map I call J0 omega 1 is in J0 omega 1 of X. Okay. Okay. This guy is saturated. Why does this not work? The non-stationary ideal on omega 1 is saturated under MM. Okay, so we have that G0 is N0 generic for forcing with the M0's version of the non-stationary ideal. Okay, and I should write a plus here. Okay, but that means I can take the generic alter power of N0 by G0, and because we derive G0 from that map, I will have a factor map, right? So I take N1 to be the generic alter power of N0 by G0, and because I derive G0 from this map, I will have an embedding which goes back from N1 into H theta, so that the whole thing commutes. Okay, and then I'm back to the very same situation. So I have an embedding from N1 into H theta, okay? And I can derive a G1 from that map and I know that because ns omega 1 is saturated, the derived measure is again generic, and so on and so on. So what does that all mean? I draw the picture again. Right, so we have h theta here. We have n0 here. We derive from that g0, so this is the alpha power of n0 by g0. So g0 is derived from this map. I call it n1. It's so it goes back to here, and we repeat the process. We always derive the next measure from the embedding, and by the fact that the ideal is saturated, we always know that this is generic. Okay, so we can keep going. Okay. N2 goes back here, and so on and so on. And you can pass through the limit stages very easily. So on the left side, what we actually, when does the process finish? Well, it finishes when we reach omega 1, then omega 1 gets mapped to omega 1. There is no critical point anymore, and you cannot derive any further measures from omega 1. Okay, so this is the picture. Okay, so now it turns out, okay, we have that C is an element of x0. So this is now our tower. Okay, so the tower we are interested in now is that the xi's I less than or equal to omega 1, where this is actually the range of the map j I omega 1. So if we have a typical and I here, right, then here is the map J. Here is the map J I omega 1, the factor map, okay? And this is our new tower, okay? And we have that C is an x0. Okay, so now N0 is a countable structure, right? Okay, so now it's a matter of fact, which I don't want to prove, but this is not hard, and it comes from descriptive set theory, which shows that if you take, so this is a countable structure, let X be real coding it. Okay. Then so if you have an alpha, which is X admissible, or if you want, just think of an alpha so that L sub alpha of X is a model of CFZ. Okay, so L alpha of X can see N0. It does not necessarily see this iteration, which is here on the left-hand side of this picture. But it is true that alpha must be a closure point of the iteration points of the sequence. Okay, so it is then true that alpha is a limit point of the set of omega 1s of ni's for I less than omega 1. So in other words, if you take X, you can sort of guess iteration points from the iteration on this left-hand side. You can guess at least a sub-club of omega 1s of ni's as just the X admissibles. Okay, but then what does that mean, right? So now if you have an X admissible, then you are a limit point of the omega 1s of the ni's, but every omega 1 of ni is in turn a limit point of C, as we observed before. So every x admissible is a limit point of your originally given club C, and therefore the x admissibles are contained there, right? So you proved admissible club guessing. Now, we did not give this argument here. And this argument is easy, but it's a little bit more delicate than what can be seen on the surface. Namely, at this point, up to this point, it seems like we only use the fact that NS is saturated. But here, in order to prove what's here in the box, we need actually a little bit more. We need at least that, let's say, there is a measurable cardinal in the universe, or at least that the power set of omega 1 has a sharp in order to draw the conclusion, otherwise it's false. So this is a fact from descriptive set theory, which uses the fact that N0 is iterable. And that's a non-trivial fact that it's iterable. I mean, there is this one particular iteration of length omega 1, which is drawn here in the picture, but there might be other generic iterations of N0 which lead to an ill-founded structure. And we have to rule that out, and only if we can rule that out, then the thing in the box is true. And in order to show that, we need to go back to the argument which we had for the generic iterability of V. The generic iterability of V was shown by this argument where we minimize this triple, blah, 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 but it's important that we work with a proper inner model. We couldn't have done the same argument with a countable structure. You know, a countable structure is too short. It does not see anything, not even generic extensions of it see, you know, the generic extensions of these countable structures, they can at most see generic extensions of that height. It cannot see a generic extension of any longer height above the height of that model, any longer iterations which are beyond the height of that model. Okay, so the argument doesn't work there. So what we basically need is we want to be able to, we want to make sure that N0 can be chosen in a way that it's a rank initial segment of an inner model of set theory, so of a class-sized model. And this is where sharps come in. So we need that H theta sharp exists, and then we take a collapse of the whole situation, and then actually N0 sharp exists, and you can, and then by the fact that you have the sharp, you can iterate the sharp out of the universe, and you will get a proper inner model which extends, which has N0 as a rank initial segment, and then you can run the proof that N0 is actually iterable. So this is something which we did not do, but a subtlety which one has to do. Okay. Now this was the, or this is a good moment. Is there any question to what we have been doing? So we have been now doing, so I showed that admissible club guessing implies that omega 2 is Aleph 2, and then we showed that admissible club guessing actually follows from the fact that the non-stationary ideal on omega 1 is saturated, plus a little bit more, plus measurable cardinal or sharps, which all follows from Martin's maximum, as we did not show. Okay, now I want to give a more complicated, or at least sketch a more complicated argument in the remaining half an hour. Is there any question at this point?
Is this a strong statement true? If X is omega 1 sequence of countable or admissible ordinals such that any element is admissible relative to the previous elements, then there is a real X such that these ordinals are exactly countable admissible ordinals in LX.
So what do you mean that the next thing is admissible with respect to the earlier?
using the previous admissible ordinal as parameters, and so admissible.
Yeah, but then they are just L admissibles.
Yeah,
no?
yeah.
So you consider the class of L admissibles?
Yeah, yeah. Just omega-1 sequence, just generalize the Jensen's result, maybe.
Okay, could you then repeat your question? So
If X is omega-1 sequence of countable admissible ordinals.
Yes, in omega-1.
Every element is admissible relative to previous sequence of admissible ordinals. Then
out to the whole sequence.
Yeah.
Yeah, but that's okay. But even that only seems to say that you are. So, for instance, the L admissibles, right? Just the admissibles, the countable admissibles satisfy your hypothesis, right?
Yeah.
Okay.
Yeah. Then there's a real X. Then there is a real X such that in Lx every countable admissible such that the ordinals in X are exactly countable admissible ordinals in Lx. So this may look like a stronger version of Woodin's club guessing.
Oh, I see. So you want, okay, for every such, I mean, okay, of course, if you look at all the L admissibles, it's completely trivial, but now you have a sub-club of that, and now you want a real X.
Yeah.
So that the X admissibles are exactly the elements of.
Right.
I think that's only for countable many admissibles. You can use a real to code that.
Yeah. For countable is true because Jensen's result. I wonder how about this result?
Yeah. I don't know the answer. Yeah.
Okay.
I don't know if the answer is known or if is it open or.
I don't know.
Yeah,
because
I don't.
This result then. Let's remind maybe it's similar to Jensen's result, and I don't know what can be generalized.
Okay, yeah, I don't know the answer.
Okay.
Okay. Okay, we don't have that much time, but a little bit of time left. So I would like to present to you a very rough sketch of a more complicated argument, how to prove that. You may think why it's complete craziness to give a very complicated argument for a statement which can be proven in a much easier way, but as I said, it turns out that this much more complicated argument can be used to show a more powerful result. Okay, and for this I want to go back to an argument from my paper with Ben Claverie. And what I want to do is I want to force the existence of an iterable structure M, the countable, sorry. So what I mean by that, M is a transitive model, let's say of ZFZ, countable. I is, from the point of view of M, a normal precipitous uniform ideal. Iterability means, right, that you can force with the positive sets of I, take the generic alter power, it's well-founded, and you can repeat the process. I mean, one step is okay by the hypothesis on precipitousness, so successors are okay. But the point is, the hypothesis of iterability also says that at limit stages are okay. And because M is countable, that's not automatic, in contrast to what we proved for V, which generalizes to models which have all the ordinals, it's not trivial if you take countable structures. Okay, so I want to force the existence of a countable iterable structure together with an iteration, a generic iteration mi epsilon ii of m. So the iteration is supposed to have length omega 1. Okay, let me write it down a bit nicer. Such that the last model m omega 1 is actually equal to h omega 2 epsilon, the non-stationary ideal on omega 1. And here there is a v here. Okay, so you cannot have this situation in v itself, right? Because omega 2 is omega 2, so it's regular. So if you start out, so m0 is just m, that's countable as it's written down. So all the mi's for I strictly less than omega 1, they are all countable automatically. And therefore, m omega 1, so supposing that this situation existed in V, the size, the cardinality of m omega 1 would be aleph 1, but h omega 2 is a bigger structure. So in V, you cannot have that situation. In fact, if you think a little bit more carefully about it, the ultra power embedding from M0 to M1 is cofinal in the height of M1. The height of M0 is kind of, M0 iterates into h omega 2, so the height of M0 is kind of the h omega 2 of M0. Okay, all these iteration embeddings are cofinal. So the map from M0 into h omega 2 is cofinal in the ordinals. So this generic iteration adds an omega cofinal sequence into omega 2. So it has the same effect as number forcing in that it turns the cofinality of omega 2 into omega. But we also want to design the forcing in a way that the forcing, because it's supposed to be useful in the context of Martin's maximum, we want it to be so that the forcing does not preserve stationary sets. So do it via a forcing. Which preserves stationary subsets of omega 1. Okay. So what I want to do in the remaining 20 minutes today is discuss aspects of this forcing. And then in the first part tomorrow, I will try to finish off the sketch of how the whole thing works. And then the second part, I will introduce the ℙmax forcing and star. And then we will go back to the argument and we will argue that that particular forcing actually also produced a proof that star follows from Martin's maximum. Okay. Okay, so this is our goal now. We want to force this kind of situation. Now, the first observation on this entire thing is, if one reflects on it, it's not hard to see, it's not too difficult to see how such a situation may be forced if we forget about stationary set preserving and if we forget about not collapsing omega 1. So if we allow omega 1 to be collapsed, we may just collapse omega 2 to become omega, and then one can argue that there, in the forcing extension, there is actually such an iteration. But then the meaning of omega 1 changed, and then that's not really useful what we did. And also for the application to MM, we always want to work with stationary set preserving forcing. So this doesn't make any sense. Okay. So we have to do it in a more gentle way, in a more careful way. And it turns out that the idea of Jensen's L forcing is a very good one. And it's actually some kind of universal method for many goals you have in set theory when you want to force something. After all, what does it mean that you want to force something? It means that in the generic extension, you have a certain property holds true. These properties are verified by some models, some, let's say, transitive models which exist in the generic extension. So here, what we want to have is a specific generic iteration to exist, right? So we can think of what we want to achieve is just a model in the extension of size, let's say Aleph1, which thinks that there is this iteration and which thinks that M0 is iterable. The iterability of M0 is a statement which is absolute between V or any V where this model exists and an inner model of that universe which has omega-1 contained in it. Okay, so so the way we can think of what we have to achieve is we want to force the existence of an Aleph1 sized structured transitive which can see such a generic iteration and can see that M0 is iterable. Okay, and we want to do it in a way that we preserve stationary sets. Okay, so we want to see just, we want to produce a model. So what does the model have to satisfy? The model has to be transitive, and the model has to satisfy a certain theory, and that's all, right? And we want to do it in a stationary set preserving way. Okay, so how do we get such models? One way to get these kinds of models, if you think back on the proof of the Gödel's completeness theorem, what he does there is, well, he constructs a model as a term model, right? You want to produce a model of something, and this is exactly what we are going to do here also. So we want to achieve the model in a forcing extension by forcing with finitely many pieces of information about the truth, about finally much information about the sentences which are supposed to be true in the model, plus a proof of the fact that the model is going to be transitive. So for instance, you can simply think of the situation as you force with finitely many statements which you prove will be, which you promise will be true in the final model which you try to achieve, whose existence you try to get, together with the fact that, for instance, if the sentence, I don't know, this or that guy is an ordinal as part of the theory, part of your forcing condition, then you assign some ordinal to it and you promise that this will be respecting, if one guy, if the theory says that this is bigger than that, then the assigned ordinal here is bigger than the assigned ordinal here. Okay, so in that way, you want to force the existence of a model by forcing with consistent finite fragments of such a model. So we want to simply, we have a certain theory which we want to realize in a model. So the theory is that there is this generic iteration, and we want to turn this theory into a maximal theory which is consistent. So what we force with is simply force with finite fragments of such a complete theory. So where the proof of that the theory is consistent, where is this proof to be given? Well, you want to be able to realize, you want to be able to find a complete theory in some outer model, and that's all. Okay, so what do I say? Okay, so let's recap. So the way we think of the situation is we aim to find a transitive model let's call it n, such in a stationary set preserving forcing extension, such that, okay, I mean, right, so that h omega 2 comma epsilon comma ns omega 1 is an element of n, but not only that, n can see that there is a generic iteration mi. So what is the notation for a generic iteration? You have the models mi, and then you have the choices of the generics. So gi is supposed to be a generic for mi. Well, all mi countable, such that two things, m0 is iterable, and the last model, well, there is no last model here, but if m omega 1 is the direct limit of the mi's I less than omega 1, or rather, you know, not the direct limit of the models, but the models together with the embeddings between them, then m omega 1 is equal to the h omega 2 of v, or rather to the structure. You know, I'm thinking of structures equipped with predicates for an ideal. So the last thing is this guy. Okay. Okay, and as we said, this will be achieved with force. So think of n as a term model, right? By scholemizing, we may assume that that n is, for instance, the hull of its own ordinals, and then everything in n is actually given by a term applied to the ordinals. So how do you prove the, and therefore n may be identified with the theory of statements which hold true in n with ordinal parameters. Okay, so you do this kind of thing by working in a language which has constants for what is to become ordinals, right? And then you have the language, you have statements in these constants, and how do you prove that in the end a maximal consistent theory will give a transitive structure? Well, you also assign to these constants, which are supposed to become ordinals, assign actual ordinals. Okay. Okay. So the forcing will consist of finite sets of sentences. Okay, I'm gonna write it on the next page. Okay, the forcing will consist of finite sets of sentences in a language describing the full theory of such a model, plus starting to prove that this model is well-founded by ranking the constants, okay? Okay, so a typical element of the forcing will be a finite set of formulas phi, and then you have constants c, I don't know, I0 up through Cik. Okay, so you might want to say that a finite list of such things is in the theory, and you also want to say that I also want to rank, so I have a finite function which maps a constant which I use in the finite sequence of formula up here. I map it to some true ordinal. Okay. Okay. What is the promise? The promise is such that somewhere in some outer model, so in some outer model, this bit of information this finite bit of information can be extended to a maximal consistent theory plus a proof. If you have a maximal consistent theory, you can define the term model, and because we have all these functions which assigns actual ordinals to the constants, we will have that it's actually well founded. Okay, plus a proof that the model which arises is well founded. I agree that I'm getting a little bit sketchy here, but you see, if you write everything down, which I'm now trying to say, it's taking forever, and maybe it's not a good way to do that in this context. So I'm trying to give you the idea, and then if you want, you can go to the paper and read it. So I'm trying to give you the idea. So the key idea is we want to obtain a model of size LF1 in a mild forcing extension, not destroying any stationary substance of omega 1. And the way we achieve it is we just force with finite approximations to the theory of such a model, together with proofs that the model will become transitive. And we cannot simply force with finite such fragments. We want to make sure that somewhere this finite fragment can be extended to a complete and consistent theory. Okay, that's very important. Okay. Okay, we will spell this out in more detail in the first part of tomorrow's talk. We have 5 minutes left. I want to take the last 5 minutes in order to show you another technical ingredient which will become necessary in order to actually show that the forcing preserves stationary sets. And this is diamond. Okay. So the forcing we will write down will actually have size LF3, at least if 2 to the LF2 is LF3. We will assume that 2 to the LF2 is LF3. In fact, we will assume that what's called diamond omega 3 holds true, and I want to write down an equivalence to this fact. This implies that 2 to the LF2 is LF3, which is a statement we don't necessarily have from Martin's maximum, but it's easy to force it. I didn't yet tell you what it means, and in fact, we don't really need the statement, but we make use of an equivalence of that statement. So what is the statement which we actually will need? So we take diamond LF3 to mean the following. There is a sequence of Qi alpha I, alpha less than omega 3, okay, so that Q, oops. So the Q alphas, this is a tower of substructures of H sub omega 3 of size LF2. I mean, the individual models are supposed to have size LF2, so that the union of all of them exhausts all of H omega 3. There is certainly such a thing. So you just take a tower of substructures. You keep they are all transitive, right? I'm sorry, I want to write that down. Of transitive substructures of H omega 3. No problem with that. But I also want, and this is the diamond feature, I want that for every A, which is a subset of H omega 3, if you look at the indices alpha, so that Q alpha comma A alpha is a substructure of H omega 3 together with A, that's always stationary. And this is the diamond part. Okay, you can easily force directly this version of diamond, which is equivalent to the standard diamond sub omega 3 by forcing with initial segments. And this will give you this result. And this is something which we will need. This is technical but necessary. It's a technical ingredient in order to take care. We will use this we will apply this to kind of names for clubs. So the capital A will be a name for a club, and this name will have to be guessed on a stationary set, and then things work out. Okay. So our goal is to force by a stationary set preserving forcing an iteration of length omega 1 of a countable iterable structure, which moves up to H omega 2, and we will do this in this way by forcing with finite approximations to the complete theory of this whole situation. And the technical ingredient is that we will need what's called side conditions. And in order to spell out what side conditions we need this diamond sequence. Okay, and so in the first part tomorrow morning, I'm gonna finish off this construction of this forcing, and then in the second part, I talk about ℙmax forcing and the variant of this forcing, which will show the star follows from MM double plus. Okay.
Thank you, Ralf.
Sure.
Do we have questions?